Let's see, I'm sharing, I'm recording, and let's get started. All right, before I forget, there's attendance for today, and did anyone miss Tuesday, the air quality lab handout? The 22nd. Is that it?
So the recording is a little bit bad, so I'm going to re-record. I'll do the best I can. So every once in a while you'll hear me talk.
All right, today we're going to finish with ozone chemistry, and we're going to move on to aerosols. A reminder about stuff. So 227. So next Tuesday, homework number 2 is. I put up already homework number 3, which is due on March 5th. The midterm will be on March 12th. I'll give you some more information next week. And then the air quality lab is due March 21st. Okay, so obviously summit a month away, but the earlier you get started, the better. Okay. I have here, based on everyone's, I have a schedule. Okay, this can change if something happens. Let me know. But find when your talk is, right? And if anyone sees any issues now, let me know. Or if you see any issues in some time. So the first one will be March 28th. And then, 2 weeks later, after. So that's right before spring break, after spring break. And those 3 are basically not the are those the last 3 weeks? Something like that. Okay. Anyone see any issues? Okay. Let's see. April. Yours is okay. And if you're happy with it, that's good. It's a little bit difficult just because it's kind of like an overview of a bunch of stuff, right? So if you ever have issues, let me know and we can discuss it, okay? Same thing for J's. Where's J? The cloud horizontal sizes.
There's nothing really to say here. Just if you have any concerns with this, let me know.
Now, all right. Okay. Reina and Jamiza, right? Did you get to sign? Okay, you need to sign. You'll this. I need to get yours. Let's see who else. Jessica. Yours I couldn't. Let's see. The others, Pedro, and yeah. And then Yashvi, I'll ask you again later, or if you're listening to this, let me know. Okay, any other issues? All right, like I said, anything comes up, let me know. Okay, so.
Here we're talking about if there are any chemicals that we want to add to the list. Last time we added isoprene and terpenes. These are what causes smells. The downside is that they can form ozone. That is isoprene that I just drew up there. If you have 2 or more of those are terpenes. Notice that they have those double bonds, and that's what makes them so reactive and so good at producing ozone. The second compound we have up there is OH, hydroxyl radical. That's the detergent in the atmosphere. It gets its name, detergent in the atmosphere, because it reacts with everything with a hydrogen and removes it from the atmosphere. So it's very important. It's what kicks off a lot of the chemistry that occurs in the atmosphere. All right, and then we got into a review of the short-lived air pollutants. The first is NOx, which is NO and NO2. The key thing is that those two cycle between each other. So NO can be released in the atmosphere, that gets converted into NO2, and then back to UV. And that cycling is important for ozone production. So we have NO going to NO2. The NO2 photolizes to form an oxygen atom, which forms that ozone. But then you have OH and HO2, and HO2 basically recycles the NO back to NO2, right? So you have this conversion that you put into the atmosphere VOCs and NO, and you get a lot of ozone coming out. Now this is on also a review of maximum incremental reactivity. This was research done in Riverside, and basically trying to understand how much ozone you can form based on the VOC. So not all VOCs are the same when it comes to producing ozone. And a key thing is, if you notice, ethene produces more ozone than ethane. And the real reason is because ethene reacts a lot more with OH than ethane does.
Here, but isoprene would probably be something like 20 grams of ozone for every. Right? You have this.
All right, and so ozone in the troposphere, the concentrations vary based on the season, during the day, and location. So during the day, you can see here that one of the key things is that the reactivity is nonlinear. What that means is if you increase the amount of NOx, right, which is on the x-axis, you actually get to a point where you have too much NOx and you lose ozone. Then we started talking about isopleths. Isopleths are where you basically have a two-dimensional way to show something that's three-dimensional. So here we did this last time. Basically, if you have cheese and bread on the axes, right, the more cheese you make, and so in that blue circle, those are places where you have not enough bread. It's bread limited, right? So if you wanted to make more bread sandwiches, you need to increase the amount of bread. The orange place, that is cheese limited. That's a place where you have a lot of bread, not a lot of cheese. And the key thing is with this example, which obviously we're going to move on from, if you add either more cheese or bread, you'll always be able to either make more sandwiches or have the same amount. That's not the same for ozone, right? In ozone, actually, at certain places, if you increase the amount of NOx, you can actually make less ozone. So this is an ozone isopleth. We have NOx in ppm on the y-axis and VOCs on the x-axis. And the different lines correspond to different ratios of VOCs to NOx, right? So that center line, that's where we have 8 times more VOCs than NOx. Yeah. And so right now, right, those are just lines, right? There's nothing on here. You can see that bottom right quadrant, that's a place where we have a lot of VOCs, not enough NOx, so that's NOx limited. That upper left area, that's where we have a lot of NOx, but we are VOC limited if we're trying to make ozone. Remember, we don't usually try to make ozone, but yeah, that's what we're going to be looking at. Now, based on modeling, what you can do is you can say, okay, if I have this much VOC, this much NOx, how much ozone am I going to make? All right, so that red line corresponds to, hey, if I have this much VOC and NOx, I will form 80 ppb of ozone. Right? So anywhere on that line, if I'm below it or below it to the left, I make less than 80. If I'm inside, above it, or to the right, I make more. The blue line corresponds to 160, the next red line 240, etc. Right? So you can see that where you are determines what you're forming. Notice, by the way, that if you are at 0.3 ppm of VOCs, right, and you go up in NOx, you can actually get it where you produce less of the ozone. And that's what's so important with these cases. All right, so let's now say we are at that yellow star. So it's a city that has an average NOx of 200 ppb or 0.2 ppm and 0.3 ppm of VOCs. So that's where the yellow star is. It's just outside of the 80 ppb line. So that means it's made about 75 ppb of ozone. So what happens? If we reduce the amount of NOx, right? So what that means is we go down in the amount of NOx. So move that yellow star down. Well, notice now it gets on the opposite side of that 80 ppb line. And so we're actually forming more ozone. We're forming 80 ppb. Whereas if we reduce the amount of VOCs, right? So we move that yellow star towards the left, right? That's less VOCs. What happens is we're getting further away from that line. So that means we're reducing the amount of ozone formed. Okay. So in this location, if you just say, hey, I'm going to reduce NOx, you can actually form more ozone. Okay. That doesn't quite make sense, but because it's nonlinear, because you have other reactions that occur, you have to be careful. And so this is a location where it is VOC limited, right? So in VOC limited, you reduce VOCs to reduce the amount of ozone formed. All right, so this kind of summarizes it. summarizes it. So if you are in a VOC limited region, right, so where that yellow star is, reducing VOCs reduces ozone. Reducing NOx can actually increase your amount of ozone. If instead you're in the NOx limited region, right, so down in the bottom right corner, reducing NOx reduces the ozone. Reducing the VOCs actually has no effect. Okay, so it's not like it increases ozone, but it just has no effect. So there, you really want to reduce NOx. So VOC limited, you reduce VOCs to reduce ozone, and NOx limited, you reduce NOx to reduce ozone. All right, now here on the slide are two different isoplaths for two different cities, and it depends on the VOC mix and weather and other things, but definitely the ozone isoplath can vary from place to place. And so reminder that ozone isoplaths are used to say what is the maximum ozone that can form from a given initial mixture of VOCs and NOx, right? And it's based on modeling. So that's it for ozone. Remember, VOCs plus NOx plus UV light gives ozone. You need to know the details of that, but that's just the big overview. Diurnal trend, you will have the highest in midday. Seasonal trend, highest in summer. Now, if you want to reduce ozone, it depends on if you're VOC or NOx limited, right? So in cities that are regions that are VOC limited, you reduce the VOCs. If you are in a NOx limited region, you reduce NOx to reduce the ozone. Ozone has a lifetime on the order of hours, so that means you can get transport from one region to another, right? So ozone made in LA can make its way to San Bernardino. Pollution from San Bernardino could make its way to, like, let's say, Palm Springs.
Transferred from the west to the east, right? Well, pollution from China, at least ozone pollution, has very little effect on why. All right.
All right, so we just finished up with ozone. It's a secondary source. It causes lung damage. It comes from NOx and NMHCs. Another name for NMHCs are VOCs. So now if we go to SO2 or sulfide per dioxide in the atmosphere.
SO2 comes primarily from fossil fuels, which are anthropogenic, and volcanoes, which are natural. So this is different than some things, right? Some things only come from humans. This is something that comes from either. In fossil fuels, sulfur is naturally in coal and oil. So if you burn coal and oil, you get SO2 coming. Why is it important? Well, once it's in the air as SO2, it can form aerosols and also acid rain. We haven't really talked about either one of those much, so we'll get to both those in a second. This is the amount of sulfur from different sources, right? All of these, so you can't quite see it. This is coal, natural gas, oil, right? And then these are other things, right? So notice the amount of sulfur being emitted went from almost nothing up to, 70,000 kilotons.
All right, so it cut off again. So it peaked around in the 1980s or 70s, 80s, and the key thing is that since then, the amount of sulfur being emitted has reduced, and you can see that in the coal and in other things. Now, this decrease has been especially in the United States. So these charts show for the different regions the decreases. So you can see in Europe from 1990 to 2015, we're seeing a decrease in the amount of sulfur.
What about East
Right?
Asia?
Same thing with North America.
Pretty much.
But in East Asia, primarily China, you can see it's fairly flat, right? It's been fairly constant over that time. And so that's why it hasn't been more dramatic. Okay? By the way, the numbers themselves aren't important, but it's good to know about the trends, right? We had that peak in the 80s. Now we're starting to see a decrease,
right? 1990, 95, 2000,
especially in Europe and in North America.
Right? And Asia, East Asia, is remaining fairly.
Notice, by the way, that that yellow, that's India. So it was increasing, but not as significant as the others. So there are two types of coal. There's what's called bituminous and subbituminous. And those types of coals have varying amounts of sulfur. So wait till that comes back up. So here we can see that in black or in very dark brown are locations with bituminous coal. The medium brown is subbituminous, and then light brown is other coal. And so what you can see is that in the east, right, especially West Virginia, Pennsylvania, there's a lot of that bituminous coal, and that has a lot of sulfur, right? Other types don't have as much sulfur. So when you burn them, you don't get as much SO2 coming out. All right, so what happens once the SO2 gets into the air? Well, the SO2 can be oxidized to SO42 minus sulfate. And this can either be by heterogeneous formation, that means it's in the aqueous phase like in clouds, or it can be catalyzed by metals. Once you form that sulfate can react with ammonium in the gas phase, and that can form ammonium sulfate, NH42SO4. And that can be in the aerosol phase. So you get these gas phase emissions, they form ions, and then those ions form two aerosols.
You can form this sulfate. All right. Once you have this sulfate ion, it can react with ammonium to form ammonium sulfate. Okay. And because NH4 plus, and this is SO42 minus, you get NH42 SO4. Right? This leads to acid rain, which we'll talk about soon. And this is just aerosols. When you guys think of coal, where do you think of in the United States? Appalachian area, West Virginia, right? Western Virginia, Western Virginia, Pennsylvania, right? That's all where we think of coal mining, right? If you ever watched Hunger Games, that's where District 12 is, right? In the future, they're thing. Right? Okay, so coal, right, primarily is a thing there. That's also where it's primarily used as an energy source. Okay. And so on the right, on the top there is from 2000 to 2002, the mean amount of sulfate in aerosol. Okay. So red is high amount of sulfate, blue is low amount of sulfate. So what do you see? Well, clearly sulfate is an East Coast issue, right? You have all those factories, right? And you see really high sulfate. On the West Coast, we don't really see it because why? We don't use a lot of coal. Also notice, what direction does the wind go? West to east or east to west? West to east, right? So that's why you see, as you go east, you see it kind of like keeping on there, right? Because sulfate can be thing and can be transported east, right? It really doesn't transport west. This is in 2008 to 2010, okay? Same color scale. What do you see? A lot less, right? Whereas before we were seeing up to 5, micrograms per meter cubed. Now, this yellow, which is the high spot, there's a little bit orange there, but it's about 3.7. So it's why is that? Less coal usage. And what they can actually do is, even if they produce the SO2, they can scrub it. Okay. So instead of on your pipe, right here, before it actually gets emitted, you have a scrubber which removes out that SO2. All right, so sulfur dioxide can lead to aerosols. It can also lead to acid rain. Okay. All right, so if you have SO2 in the atmosphere, it can be oxidized to SO3, and then it can react with H2O to form H2SO4. H2SO4, you can get the same thing occurring, or similar thing occurring, if you emit NO2. NO2 is going to give you HNO3, right, which is nitric acid. So if this sulfuric acid and nitric acid gets produced in clouds, you're going to get basically an acid wash of anything downwind of this power plant. Yeah. Is a on the top right, that's a Europe. Downwind from these power plants, you basically get stripping of the vegetation, right, because of all that acid rain. It also affects architecture. This actually is a statue, but if your building is made out of stone, like it is in a lot of Europe, right, it can cause. That water also gets into your streams, right? And so now your streams are now more acidic, and that can do. This is the pH of precipitation in the United States in 2002. Okay, so green is pH above 5.3. Once you get to white and then oranges, those are below 4.8. Okay, so you can see the Western U.S. all has pHs in 5. The Eastern U.S., at least in 2002, all has these lower pH. Okay, this is well, I don't have it on here. That's basically the same location where we saw the highest amount of SO2. Okay, so you have this SO2 being emitted, and you get acid rain being produced. On the left, this isn't the pH, but it's the sulfate ion concentration. Okay, so it's looking. So this is 1985. So you can see the highest sulfate in picture, right, in 2008, right? So you can see that dramatic reduction where the sulfate has gone from, what is this, above 3 milligrams per liter to now it's, except for this hotspot, it's generally below 1. Well, even these small changes have an effect, right? Your vegetation has are effects. Beijing, or sorry, China in general, in 2017, right? This is their precipitation, and you can see that these really high levels, low levels of acidity, or high whatever, right? West, you don't quite have that. Why? Because you have
All right, so SO2 comes from coal and oil. It also comes from volcanoes, but primarily coal and oil. And this can cause acid rain and aerosols. Acid rain, not as big of an issue in the United States anymore, but in other locations like China, it still is. It does still produce aerosols. Okay? So now let's talk about aerosols. All right, so what are aerosols? Aerosols are solid or liquid particles suspended in the air. They're also known as particulate matter, or PM. They can come from anthropogenic or natural sources. You can see some of them here. The volcano, natural; the car, anthropogenic. Some things, they're a mix. That forest fire, we don't know. These aerosols can either be secondary. What that means is they're produced in the atmosphere, or they can be primary. Look at the smoke coming directly out of that tailpipe.
They can come from natural sources or anthropogenic sources, right? We can see here, this is obviously anthro, right? Something like a volcano would be natural, or trees or dust. A fire could be either one. You can have either primary aerosols Or secondary aerosols. Secondary meaning it gets produced in the air.
All right, so we have variable sources, as you can see, and this leads to variable properties. And so some of these properties we'll talk about are what they're composed of, what makes them up. So composition, their color. You can see that some are whiter in color, some are darker in color, and then also their size. All of these can have different different effects depending on what we're looking at.
Variable sources and therefore variable properties.
This is a chart of different sizes for aerosols. So we have some as small as nanometer, 10 nanometer and even smaller. And we can have things that are over a micron in size, right, or over 1,000 nanometers. The bigger things like pollen and dust, you can even get these big enough that you could actually see them with your naked eye. But the really small things are invisible. And it's not quite true, but it's a good thing. Natural sources tend to give you large aerosol, whereas anthropogenic tend to give you the really small aerosols. All right, so why should we care about aerosols? There are three reasons why we should care. The first two have to do with the fact that aerosols interact with light. Oh, I'm restarting the computer or restarting the PowerPoint just because there was an issue with the pen. Okay, so aerosols interact with light. They can do this in one of two ways. They can either scatter light. Okay, so let's say you have incoming light, let's say the sun, that will hit the particle, and the particle will scatter that light in all directions. Now, this depends on aerosol size. The bigger it is, the more it scatters light. The second type of interaction with light is absorption. So here, the light hits the particle, it gets absorbed, and what happens is it doesn't keep that light. That light actually gets re-emitted as infrared light, and that heats the atmosphere. Now, whether you have absorption is really dependent on the aerosol composition, what it's made of. Now, both scattering and absorption are in the units of per megameter, or megameter to the -1, or 1 over megameter. It's weird units. What it means is, hey, if you add a megameter in distance, how much light is removed from it? So we have scattering and absorption. The sum of those is called extinction. So extinction is scattering plus absorption. Oh, another thing that affects absorption is the color of it. So the darker the aerosol, the more likely it is to absorb.
which one, it's July, it's 100 degrees. Who made the smartest choice going to the beach? What? The white. Why? Because it doesn't get as hot, right? That black hoodie, it's gonna get really hot, right? Your white shirt scatters that light, right? That's why it's white, right? White means we're seeing all the colors, like light hits it, all of it gets emitted. That's black because it's not giving off light, right? All of that light got absorbed by the sweatshirt, okay? The same holds true for particles, right? This right here, this is absorbing light. This is scattering light. Okay? Yeah. All right, the sum of scattering and absorption is emission. Or sorry, extinction. Extinction, right? Think of it, hey, extinguish light means you're not seeing as much. So extinction equals scattering plus absorption. The units of this, but it's inverse megameters. What it basically says is in one light is all right, so why should we care? Aerosols reduce visibility. So that's Houston, Texas on a dirty day and on a clean day. Why can't I see these windows right here? All the windows here, but here I can see them. Well, because light that gets reflected off of that building and coming towards me or where the camera is, right? In that top, there's particles in the way that remove that light, right? Here, that light coming off there, I see it, and so I can see the depth. Windows are, okay? Same thing if we go outside, sometimes we see the mountains, sometimes we don't, okay? This is San Gorgonio Wilderness, which is kind of southeast of us, right? I think it's kind of where, if you're going to Palm Springs, that direction, right? This is the same location, the same camera. If it's 12 per megmeter, which is very clean, right? This is 98 per megmeter. Notice going between those, this mountain starts to go away, right? That's because air. This is something called Improve, which is the national parks really care about this because they're really concerned about how urban locations affect national parks, right? Why? Because you go to national parks to see beautiful landscapes, not to see that on the right. Okay. All right, so that's the first reason why we care. The second reason why we care is okay, we'll talk more about this when we get to climate change, but if you have incoming light, if light gets scattered, it cools the atmosphere. If light gets absorbed, it warms the atmosphere. Same way, black hoodie warms you, white jacket at least doesn't heat you up, right? Maybe it cools you, maybe it doesn't, right? Or think of what this is called the direct effect. Okay. Aerosols also play an indirect effect on our atmosphere. Okay.
We can also have what is called the indirect effect. In the indirect effect, changing clouds, right, or changing aerosols, putting aerosols into the atmosphere, changes cloud properties. So remember that aerosols, small solids, water condenses on them, and that's how we get clouds. Eventually, those clouds get so big, cloud droplets get so big, they can form rain. Well, if you change the amount of aerosols, you can change cloud properties, right? You may have more clouds or you may have less clouds. You may have brighter clouds, or those clouds could just last a longer time. This is actually one of the students is looking at actually trying to change cloud properties. Annabella with climate intervention, right? So that's what her paper is looking at.
Seen it, but probably putting more aerosols into it. Right? Let's get back. Where are we? Here. Okay. So this is a figure we'll show later. This shows the things in the atmosphere that warm the atmosphere and things that cool the atmosphere. Okay? Up top is CO2. CO2 warms the atmosphere. Next we have CH4. That warms the atmosphere. This right here, so this line right here, everything on this side warms the atmosphere. Everything on this side cools the atmosphere. Okay? CO2 warms the atmosphere. That's all we hear about when we talk about climate change. We talk about CO2 increasing. Rightly so. We'll get more into that. But notice, this right here is aerosols. Right? Aerosols, in general, cool the atmosphere. Okay? Clouds also cool the atmosphere. You can't quite see it. We blow it up once we get talking about it, right? This is the error bars for that cooling effect. They're huge. Why do you think it's so hard to figure out the effects of clouds, aerosols on clouds on our environment? Because clouds are really hard to measure, right? Clouds are really hard to understand, right? Why? Because A, you have to go up to that, and if you fly through it, you disturb it, right? And clouds change really fast, right? CO2 doesn't change. It remains CO2, so it's easier to understand. Clouds are a huge cooling effect and are very uncertain, right? In fact, they're the most uncertain term when we talk about climate change. All right, so that was the second reason. What was the first reason? Reduce visibility, right? Reduce visibility, have an effect on radiation budget. The third reason is that aerosols affect human health, right? And actually all animal health, but really, human health, right? So aerosols cause deaths because they increase cardiopulmonary disease. They cause 5% of deaths due to lung cancer and due to infection. On human mortality. Their health effects really depend on their size. Yeah. If you go to the beach, right? And the lifeguards come by in their truck, right? And they pick up all that sand and you breathe it in. What do you do? Almost immediately, you start coughing, right? Why? Because dust is really big, right? And so or sand is really big. So, and when that sand gets into your throat, you have defense mechanisms in your throat, right? Coughing and cilia, right? To remove those large particles. Okay. So large particles, let's say greater than 10 micron, don't really make it into our body, right? They either get removed in the cilia or we cough it up or something like that. But if it's small, it can make its way into the lung, right? So if it's smaller than 2.5, it can make it into the lungs. If it's smaller than 1, it can make it into the alveoli, right? If it's really small, it can even make it in the bloodstream, right? So the smaller the aerosol, the further down into our lungs it gets. Okay. Large aerosols are things like dust and sea salts. Smaller, like and from organics, from sulfate. This isn't quite true, but natural sources tend to produce large aerosols. Anthropogenic sources tends to produce small aerosols. Because of the huge effects of aerosol size, we have these different cutoffs, right? PM10 is the mass of all particles smaller than 10 micron in size. PM2.5 is smaller than 2.5 micron. PM1 is smaller than 1 micron. Okay? It's designed, or if you look at it, right, PM1 will always be less than PM2.5. The same way that PM2.5 will always be less than PM10. Why? Well, if I have the entire population and I say, okay, what's the entire population younger than 10 years old? And what's the population younger than 20 years old? The population younger than 20-year-old will be bigger than the population bigger than less than 10, right? Why? Because 20 includes those younger than 10. Did that make sense or did I confuse that? Right? So this includes this. This includes this. Aerosol scientists, you have to understand the things on the right don't. But just to say that aerosols come not in one size, they come in a size distribution. Okay? So it's not like all dust is one size. There's some that's a little bit bigger, right? There's some that's 2 microns and 10 microns and
All right, so we can differentiate aerosols based on their size. So we can say that PM1 is particulate mass of all particles smaller than 1 micron in diameter. We have PM2.5, which is particulate mass smaller than 2.5 micron diameter. And then PM10, which is particulate mass, the mass of all those particles smaller than 10 microns in diameter. These are all measured in micrograms per meter cubed. And a key thing is that PM 2.5 is part of PM 10, right? So PM 10 encompasses PM 2.5. So PM 10 will always be bigger than PM 2.5. All right, so going back to the health effects, It really is dependent on the size. And remember what we said, natural tend to be bigger, anthropogenic tends to be smaller things. In the small ones, PM1, smaller than 1 micron, those can get down into your lungs. And it's not just that they get into your lungs and they cause blockage, etc. They can also carry with them a lot of damaging things, such as PAHs, polycyclic aromatic hydrocarbons, which are on the right? Polycyclic meaning you have aromatic ring, but you have multiple of those, and metals. And these can cause damage once they're in our body. Where do these come from? Well, combustion in our cars, very high temperature, very high pressure. You get a bunch of chemical reactions occurring. And metals, or engines, are made of metals. So when you have combustion, you're also having some metals being emitted. Another source of metals into our atmosphere are brakes. Every time you brake your car, you're rubbing off a little bit of metal. That's why eventually your brake pads wear. So that creates some metals that gets in the air, tends to be small particles, and we breathe it in.
Okay. Where do these metals come from? Well, what's an engine made out of? Metal, right? Your brakes, every time you brake, you're producing a little bit of metal, right, that's shaving off there, right, into the air. Okay. So these metals can cause oxidation to occur in the body, right? And this can damage DNA and RNA, right? So you're getting these organics coming out of there, you're getting these metals, and inside your body, they're causing a lot of damage.
At this point, these are the 3 reasons why we care: reduced visibility, the effects on radiation budget, climate change, and health effects. And so I asked the class, what is the most important of these 3? And no one picked number 1. I think most people picked number 3, and a few picked number 2. And in reality, 2 and 3 are good answers. 1, probably not that important.
How about 3? It's probably right? Term health effects, in the long term, hey, maybe the climate change is a bigger issue, right? Both those are important. The visibility, which is the most obvious of them, well, it stinks we can't see downtown LA or we can't see the mountains very well, but it's not going to affect my health. Okay. By the way, number 1, that's why California is known for its beautiful sunsets, is because of aerosols, right? Those aerosols cause scattering of the red light, which leads to those really beautiful sunsets, okay? All right, let's talk a little bit more about aerosols. And let's talk about aerosols are composed of a number of different things, but primarily sulfate and nitrate. Both of those are anions. So we need a cation to be with them. So usually that's ammonium, NH4+.
We also have magnesium and calcium. These come a lot. These minerals come a lot from dust. So you have different regions, desert regions that produce dust, and different amounts of magnesium and calcium can come from there. You also have sea salt. Sea salt is salt. So you have some sodium, you have chloride, you have some other halogens in there. You have bioaerosols or pollen, and you have organics. Organics is a broad class. Another one are black carbon or soot. Now, if we look at this publication on the right, they broke down from different locations in the world. You can see the boxes where they were sampling. What percentage they saw of all of these things. Or I think it was modeling actually. So they, for instance, that one on the far left, right over the ocean, you can see that the red dominates. That's sea salt. Kind of makes sense. The one on the top right, there, the brown, which is sulfate, dominates. Well, that's China, where they have a lot of coal, so that makes sense. In Europe, the one next to it, again, sulfate dominates. And in North America, right? So those three locations, sulfate dominates. Now, I should say this is from 2001 to 2010. So it's probably changed. Sulfate in North America has probably decreased since then. If you look at the ones in Africa and then India, so that bottom row going from left to right, you can see off the coast of Africa, mineral dust dominates. Further south, what we call sub-Saharan Africa, you can see bioaerosols dominate. And then if you look India, or I think it's actually a little bit east or west of India, you can see some minerals coming from the desert. You can see some sea salt, and you see sulfate. So you kind of see a mixture of those, just because it's kind of at a mixture depending on where the wind is coming from.
Your composition changes depending on where you are. Okay. By the way, this is a bad graphic. Okay, it's a bad graphic. Why is sea salt red? Right, sea salt shouldn't be red. Right, there are some things that like don't make sense. But anyway, we talk about organics. Right, you guys took a class in organic chemistry. Right, you know organic means 500, 1,000 different compounds. Right. So when we're talking about organics, we're actually talking a wide multitude. This is a mass spec of some of those organics, right? And depending on where it's coming from, those organics could vary, right? And there are scientists that try to understand the differences in those organics, but it's just a broad term. Generally, I'll just leave this up, even though I probably won't talk about it much. The type of organics changes with time, right? As aerosols are in the air, they become more oxidized. Atmosphere tends to oxidize. Okay. All right, so when we talk about aerosol composition, we're talking about inorganics, minerals, organics, and black carbon, right? What type composition depends on your soil, and it all location, right? Different places have different things, and because different places have different issues, what works in California to reduce pollution will be different than what works in Ohio. All right, so that is it for air pollution. What are we covering after this? I forget. We're going to. Oh, we're going to talk about measurements, etc., involved in that, right? And we'll talk about satellite measurements. All right. So, any questions on air pollution? We talked about all these different air pollutants. The key thing is are short-lived, right? What that means. Up to talk about air quality. We're generally talking about local or we were looking at those images of let's show. This right here, right? We had all those power plants in the Northeast, right? And that causes all that pollution. But once you get removed from it, it goes away, right? Why? Because that pollution can't last that long, right? Same reason I said, hey, Chinese pollution over here doesn't affect California that much. Why? Because it takes days to travel. Okay? This is going to be different once we get to long-lived species. Long-lived species can have an effect throughout the globe, right? So what happens in India or in Toledo or wherever it is has an effect on us, okay? All right, let's see. Anything else to talk about? All right, cool. All right, cool. I will see you next time. Let's go back here. That's okay.